All right, so we are going to discuss some results about the Hodgkin-Oxley reaction diffusion equation. So first, we want to prove that that n remains between 0 and 1 if it starts between 0 and 1, and the same for m and the same for h. So let's do it for n. I will just give the main ideas. So if you assume that t0 is the first time at which n reaches the value 1, and at some x0. So n of, you're right, x and t, x0, t0 equals 1. So then we are looking at this equation. So if this is true, then this cancels because n equals 1. So this becomes 0. So this is 1. So then the derivative with respect to t is less than 0. But on the other hand, since before t0 n was less than 1, we deduce that this quantity is non-negative. So this is a contradiction, right? So that proves that if at the beginning nxt is less than 1, this remains true for all time. We can prove in the same way that n will remain positive, the same for m, the same for h. Next, we're dealing with the v because there's a diffusion. So let's do some stuff here. Okay. Oh, I could just keep that. First, we are going to remark that for v large enough, oh, there's a mistake here, sorry. There's no v here. I first remark that this is negative for v large enough. Why? Because this is greater than a constant, than a positive constant, and this is bounded, so that's true. You have to go back to the original expressions of HH. You can see that. So let V capital M such that this expression is negative. All right. So here we are considering a domain which is R. Okay, then you do the same thing. Let T0, let X0, T0 such that V reaches for the first time the value Vm, and this occurs at the point x0. So at the beginning, you have that Vxt0 is less than Vm. You start with this initial condition. And then at Vx0 t0, you assume that you reached Vm. But then look, again, this quantity will be negative. Since here it's a maximum, so this quantity is non-positive. And this is a contradiction because, again, since it's the first time you reach Vm and before V was less, this is non-negative. So this is a contradiction. So you prove it like that if you work with the wall line as a domain. So if the other question was related with a bounded domain, so with Neumann boundary conditions. So let's do that. Let's do that. So I keep that, but then I must deal with the Vxx. So now so this is the same. And this is the first time. Okay, now you cannot say that Vxx is less than 0 because if this occurs at the boundary, so now you consider a boundary with Neumann boundary conditions. So instead, we will write that V of B minus H. So I will do the proof at B. As V of B minus H. So of course I should write that Vx B. So I don't write the T. Plus H squared divided by 2 plus H squared epsilon of H. And so I will replace Vxx by, so I'm going to write it by this quantity. So this is 0 because I'm working with Neumann boundary conditions. So I get that Vxx of B. So here I assume that I reach Vm at the boundary. If not, the proof works. So I have to do something if the maximum is reached at B. And so Vxxb, right, 2 divided by H squared B minus H minus Vb. All right, and I can write it plus epsilon H. Now, so again, this is non-positive. Let's do it with the red. This is non-positive. And this is as small as I want if H is small enough. So if I choose h small enough such that epsilon h plus this quantity is negative, it's done. All right. So in fact, the proof is done like that. So that's it for this exercise. Thank you. So we're dealing now with the Fitsounagmo equations. And so what's the story? Hodgkin, Oxley, Nobel Prize 1952 for their work on the giant axon squid. Then, but it has 4 equations, right? A few years later, Fitsoug proposed a model with only 2 equations. Okay, so it's more simple to analyze it mathematically. All right. And what's the idea of Fitsoug? He wanted to capture excitable and oscillatory behavior, which is present in the dynamics of the Hodgkin-Oxley equations. And this is a piece of his original paper. All right. And so, but Fitsoug was about ODE. So Hodgkin-Oxley was ODE and PDE, right? It had the propagation of the action potential. Fitsounagmo was only ODE. But of course, we can add a diffusion and look at the resulting reaction diffusion system. All right. So I will consider here for the remaining of the lecture Neumann boundary conditions, and omega is a Bonden set. It depends on R or R2 or R to the N. It depends. Okay, so here it's R2, but it depends. So for this version, if you forget about the diffusion, so the system here considered here, the behavior is the following. So if you forget about the diffusion, you have an ODE with 2 variables. All right. If you pick up an initial condition, for example, here, you go, because of the epsilon, which is a small number here, you go directly to this part and you evolve actually towards a limit cycle. All right. So here in the right part of the slide, you have u as a function of t. And here you have u and v, the trajectory u and v, and asymptotically it's a limit cycle, right? So if you're not starting at 0, 0, 0, 0, you're evolving asymptotically around a limit cycle, right? So you see, with the comparison to the Hodgkin-Oxley, this is the oscillatory dynamics that Fitsoug was looking for. So it's included on the Fitsounagmo. But okay, we start with that. I'm not considering right now the excitability, but I will come back to that later. All right. And so let's try to. So what's going on with this equation, right? What's going on with this PDE? So just to have some insights about it, we are going to do some numerics, right? So I'm sharing my laptop with you so that we can perform the numerical simulations together. So here. Okay, so now you should see my screen, right? So wait a minute. So in this program that you see, I have programmed the PDE, the reaction diffusion system. Okay. And so let's do that. So I'm running my PDE with some initial conditions, right? So for given initial condition, your PDE has a unique solution. You can prove that. And now I'm going to perform some initial conditions. So I just choose some initial conditions, some random initial conditions between 0 and 1 at each space point. All right. And I'm running the program. So let's do that. We have to wait a little bit. My final time here is 200. Oh, I need to plug my laptop. Meanwhile, I'm going to plug my laptop. So, yeah. Right. So we have to reach 200. All right, great. So we're done. Okay, so we're done, and now we are going to see the solution of the PDE, right? So for that, I have another program running. Okay. Okay, so this is the solution of the PDE. So what's going on? I'm working. So what's going on? So let's see. So you see that that's the same color. So what I'm representing here is the U, So my domain is a square with Neumann boundary conditions, and the color depends on the value of u. So if u is, for example, yellow, it's like I'm around 2. And if it's blue, I'm around -2, something like that, okay? And what you could see is that your solution is the same color on the whole domain. Your solution is the same color on the whole domain, which means that for each point, it's a constant in space. So it's moving with the time, but in space, it's constant, okay? And so basically, what's the meaning? If the solution is constant in space, this means what? This means that the diffusion is 0. So asymptotically, what you observe at each point of the space is the solution of the EDE. ODE is my limit cycle. So I can show you that. Now I pick up a point. If I pick up a point on the space and I look the solution along the time, this is the periodic solution of the ODE. Okay, and I can move so I can plot two solutions, meaning at two different spaces. For example, so they evolve along the same limit cycle. So here I have represented u and v as a function of time, the evolution, so it goes like that with the time, but there's two, and this is not at the same space, okay? And I can do also that with respect to the time. Maybe I need to reset that. You see, they're the same, okay? So the solution is constant in space, right? This was to illustrate that. So the question is there any solutions? If I tell you right now, if you don't know, and you're running a simulation, it's almost certain that you will fall into this solution, which is basically the solution of the ODE. You just forget about the diffusion. So the question, can I find other solutions? If you have some remarks, I'm happy to hear that. If not, I'm moving on. So now I'm changing. I'm picking up other solution, right? So I change my initial solution. So I choose this one. Again, so sorry, I need to run the program. So you can grab something to drink. We're running again, we're going until 200. So almost there. Okay, we're done. So again, what I'm going to show you is u, the value of u in my domain is a square, including R2, and the value of u is represented by a color. If u is yellow, it means that u is around 2. And if it's blue, it's around -2. Okay, so let's go. We're going to see the solution of the PDE. I change now what I change, just the initial conditions. It's the same equation. All right. So yeah, so to get this solution, you need to choose specific initial conditions, right? We'll get to that later. Okay. Okay. So yes, the answer is yes. We can have another asymptotic behavior. Okay, so let's move to that. All right. Okay, so here I've showed you. So this is the same solution that I've shown you. Okay. I need to transpose that. Okay. This is the first solution and simulation that I run. As you can see, everything is almost homogeneous in space. And here, it's random also, but the random is specific. And here again, I have some specific behavior. So if you don't care, if you pick up an initial condition without knowing what's going on, you're almost sure to fall into this solution. But if you start to think about it, you can obtain this one and this one. We'll deal with that more in detail in the chapter 3. Okay, today is just an introduction. But you can remark that in blue is the integral. In blue, it's the integral over the domain. So the integral of u. And you can see that here, for the spiral, the integral is 0. While here, the integral is equal to a single solution for a fixed space x, fixed point space x. That's because here the solution is constant in space. And here it's more messy and the integral is small. It's near, it's close to 0, but it's not 0. Okay? So you have a theorem. You have a theorem. So my question would be, if I wanted to challenge you, can you make a proof proving that there exist solutions that are not going to converge to constant solution in space. Can you prove that? And the answer is yes, you can prove that. And you have here a theorem. Basically, it says that if you choose some symmetry, you can ensure that the integral is 0. And if the integral is 0, this is not the constant solution in space, because if the constant solution is in space, the integral evolves as the limit cycle of the diffusion-less partial differential equation. Okay, we're going to do that more in detail in the chapter 4. Okay. Next. So, in fact, Fitsounagmo, I told you, it contains two informations, basically, oscillatory and excitatory dynamics. I've only shown you the oscillatory dynamics, but there's also excitability. And so now, to take advantage of that, I'm going to consider a C which is depending on X. But before, I need to remind you what's going on for the ODE. So again, forget about the diffusion. So on the left side, it's the oscillatory behavior for C equals 0. On the right side, I choose C equals to minus 1.5. And now the dynamics are different. So here in green, you have the null line corresponding to my function f. And in blue, I have the null line, it's u equals c, which corresponds to the second equation. So in blue, it's the u equals c, meaning that Vt equals 0. And in green, it's V equals f of u. So forget about the diffusion. That means that ut equals 0. All right. And so if I pick up an initial condition here, so the intersection between the blue and the green is the fixed point of my diffusionless equation. So if you start here, you're going to the fixed point quite directly. But if you start with the yellow trajectory, instead of going directly, you're making a large excursion before going back. And this represents the excitability, meaning that if you move your initial conditions above a threshold, you get a spike, an action potential in neuroscience. All right. So now you get the 2 points that were brought up by Richard Fitsounagmo. And we are now going to play with a PDE, which can take into account those two features. So I'm interested in that when you have cells that are excitable, in general, the excitable media is able to propagate signals. So the question is, I'm going to put some oscillatory cells in some part of the domain and look at if the signal propagates, yes or no. So now I'm looking at the diffusion. So that's what I said to you. I choose C equals 0 in the center of the domain, and C less minus 1 on the remaining part of the domain. And so I'm working with a domain AB with A equals minus 10, B equals 10. And now I'm looking, so in some slides before, I was working in R2. Here I'm working in a domain which is included in R, meaning that I'm dealing with one-dimensional space. Okay, so I pick up some initial condition and I run the simulation. First, my C node is equal to minus 1.2. What I'm seeing that is that this is converging to a stationary solution. All right. The time moves, but the solution doesn't move. It has reached a stationary solution which seems to be stable, at least numerically. Okay, now I'm changing the value and I'm taking this value, minus 1.12, right? So, sorry. Okay. Yeah, so there is some specific behavior at the center. All right. Okay, and finally, let's look at the last one. Let's stop this one and look at this one. Oh, yes. You don't see the numerical simulations.
I see the first one, but I think about 5 minutes, I see only the same screen.
Okay. Okay, and now, so those are the same parameters, but I just represented the evolution of the central cell with respect to the time. And so at the far left, the solution is constant. This is 0 because, well, so this is specific to my C of x. Then for C0 equals minus 1.12, you have the so-called mixed mode oscillations. That's the mixed mode oscillations at the center of the domain. And at the far right, you have a regular periodic solution which correspond to the so-called relaxation oscillations. All right. Any comments? No, so I'm moving on. Okay, and so finally, let's do that. Finally, now I have to share. Okay, finally, I'm going to show you again. So now my C is more complicated, and so you can get very interesting solutions. So for example, this one. So my C is depending on X, and you can get this kind of solutions. So this was intended to model some tissue with damaged parts. So for example, cardiac cells where some parts of the heart are damaged, and you get problems, and you get this kind of solutions. All right. So can I go there? Yes. So to the end, just to comment some pictures here, you can, for example, consider networks of PDEs, and look at the synchronization of the patterns, right? And so, for example, so when you choose a network, you have different kind of networks. So here we considered the so-called all-to-all networks, where all the nodes were connected. And here the point in blue represent the coupling strength at which you get the synchronization of the PDEs. All right, and so you start with 2 PDEs, then 3, until 20. So this is part of a work a couple years ago of a student coming from Vietnam. His name was Phan, and he has now returned to Vietnam. And you got this law. This was known for ODEs, but not for PDEs. So for PDEs, you get the same result, and you can also make proofs of that. And it's a law about 1/n. And so here we pick up. So we compare the values between 2 PDEs. They are coupled. So I don't put the equations here. It's just to give you a flavor. And you see at the beginning, this is the norm in L2 of the difference between those two functions. Okay, the left one is a function. It's u from R2, or from the square into R, and the same for the right. And we look at the integral of the difference between the two. So it's the difference. And you can see that when you increase the coupling strength, the difference is going to 0. So in the last row, those two patterns are the same. Okay. All right. So okay. So I think we're good for today. So this ends the introduction. And okay, you have here some references if you want. And okay, yes, see you next week.